Come on, you can start. Seriously? Honestly, wow. Taking forever. I think where we left off was the concept of breaking that tidal volume down into a component part as far as alveolar volume versus dead space volume, and then talking about how we have minute ventilation, and then that can be broken down into alveolar minute ventilation, and the alveolar minute ventilation is the thing that ultimately determines the arterial carbon dioxide level in your bloodstream. Does that sound vaguely familiar? We're in a trance. It was the weekend. I don't want to learn. I'm tired. All right, well, let's continue on nonetheless with some other components that are here. First of all, I just want to talk about the term hyperventilation and hypoventilation. It really has nothing to do with how the patient presents. So just because somebody's breathing very fast does not mean that they're necessarily hyperventilating. We're going to put specific definition on hyperventilation, being it's an increase in alveolar minute ventilation to the extent that the arterial carbon dioxide falls below a normal level. Let me say that again. If I increase my alveolar minute ventilation, we said whenever there's an increase in alveolar minute ventilation, there's an inverse response to carbon dioxide. One goes up, the other goes down. And if that CO2 falls below the normal value, then I can say that that person is hyperventilating. So I can't tell hyperventilation without a blood gas. Okay. Let's say you're who's an athlete? Exercise. Okay. I'm sorry. You're on the treadmill, right? You're running on the treadmill, and because you're producing more carbon dioxide because your muscles are burning, right? You're producing more CO2, so your body has to respond in a way to get rid of that. So you start breathing faster and deeper. But you only do it to get that CO2 back to a normal level. So even though you appear to be hyperventilating, you're not, because your CO2 is remaining in line. Does that make sense? Okay. It's a very important aspect to look at, because you'll see people say, "Oh, he's hyperventilating." Well, okay, let's get a blood gas and find out if he is. There's different terminology there. Conversely, there's the other end of that, hypoventilation, where your alveolar minute ventilation is reduced to the extent that your arterial CO2 begins to climb out of the normal range. Did we talk about the normal range for PCO2? I don't think we did, but we will. Some other terminology, definitions. Apnea, obviously, is the A being apnea. It's the absence of spontaneous ventilation. The patient is not breathing. We can have an alteration in minute ventilation because I change my tidal volume or because I change my respiratory rate. If you remember back, I'm sure you don't, because that was like way too long ago, Rick. We said that does that vaguely look familiar? Minute ventilation is equal to the tidal volume less your dead space volume. I'm sorry, this should be an A. My error. We said simply that was that. But to take into a dead space, we got to consider this as being alveolar minute volume. So if I alter this, I alter that. If I alter the frequency, I alter the alveolar minute ventilation. Either way, you can change them. Hyperpnea, it just seems like a weird word, but that's basically a deep breath. So I'm breathing at a tidal volume that's deeper than normal. Hypopnea, the opposite, a very shallow breath. We can also have alterations in respiratory rate, tachypnea and bradypnea. Tachypnea, tachypnea, being a rapid breathing rate, rapid frequency, and bradypnea being a slow. I think we said the frequency was normally 10 to 20, and this is 5 to 8 milliliters per kilogram ideal body weight. If those don't sound familiar, they will in a few minutes. Then the last thing I just want to make mention on this before we go back for some review and get into a little bit of a lab situation, which we normally don't do in this class, but this doesn't quite click until you do it yourself. But there's 3 different types of patterns that exist that one day you'll see them and you go, oh, that's Cheyne-Stokes. Oh, that's Kussmaul's. First one is bias, and bias are basically deep inspirations followed by periods of apnea, just basically these gasps. Usually we see it with patients with profound neurological disorders. Often it's just prior to them dying. Apnea. Apnea. So it's kind of a Grim Reaper standing there and these few gasps that end up happening. Cheyne-Stokes is a period of apnea followed by a period of gradually increase in tidal volume. So it gets to normal and gradually decreases, and then there's apnea again. My analogy for this, if you've seen the movie Animal House, when they're doing a little bit louder now, a little bit louder now, a little bit louder, a little bit softer now, a little softer. There you go. That's my analogy for it. Cheyne-Stokes. Again, seen with patients with some neurological issues. We also see with patients with congestive heart failure, but more on that later. And the last one, Kussmaul's respiration, is basically very deep, very rapid breathing. So you see, little old ladies that are 90 pounds that you're going, how can you possibly be breathing that fast and that deep? And keep on going. I would die after about 3 breaths. But it's a response to a diabetic issue, specifically something we're going to call ketoacidosis. We'll worry about that another day. But it's a very classic pattern of breathing. So here's graphically what we would see. Deeper than, if we look at our tidal volume here along this axis, the vertical axis, these are very deep breaths. So it's a series of gasps that are deep like that, and then a period of apnea, followed by the same pattern repeating itself. Okay, that's bias. Cheyne-Stokes is that gradual increase in tidal volume, and then the gradual decrease in tidal volume, and a period of apnea. And the cycle starts right back up again. And Kussmaul's is just this massive tidal volume. I can't even do it for more than 2 breaths without passing out. So, and as you can imagine, that large tidal volume at a very fast rate, their alveolar minute volume is huge. And it's the body's response to something else that we end up seeing. Okay. I'm not sure what this is supposed to mean, but I like it. Enough red wine to take you over the driving limit. 200 milliliters? 300. Imagine that. Okay. Now, deluge you with a lot of calculations and formulas and all that stuff, yes, you will need to know them. No, they will not be presented to you on the exam. Okay. Just got to commit them to memory, and if you can commit them based upon some, I don't know, so whatever method you end up using to get there. First one is compliance. And compliance, again, is how easy or hard it is to stretch the lung. How much give does it have? And we mathematically calculate this by looking at the change in volume divided by the change in pressure. Given a tidal volume of 600 and the pressure of 30, calculate the compliance. Well, I basically would put my tidal volume, 600, divided by my change in pressure, 30, and express that as 20 milliliters per centimeter of water. Sometimes, just because there's not a convention on this, it's expressed as liters per centimeter of water, in which case it would be 0.02 liters per centimeter of water, simply dividing that 20 by 1,000 to go from milliliters to liters. Does anybody remember what the normal compliance is? 0.1 units. Okay, liters per centimeter of water, or 100 milliliters per centimeter of water. So what could you tell me about this patient? It's low, they're stiff, right? It's going to require a lot of pressure to inflate that lung because it just doesn't want to give.
Why did you have to change to milliliters to liters?
Some places report it as liters, some places report it as milliliters. It's just, there's not a convention. You need to go kind of back and forth between the two. I apologize in advance for it. But that is just one of the many things that is nasty that I will do. Okay? Compliance. Airway resistance. Change in pressure over flow rate. So a lot of times just by looking at the formula, you can determine, or looking at the question, you can determine what is needed. So I see flow rate, I see pressure change. Well, that must mean that I'm measuring resistance. So I set it up so that I have my change in pressure, 50 centimeters of water, divided by my flow of 0.8 liters per second, and I come out to 62.5 centimeters of water per liter per second. And you probably don't remember this, but the normal value was something like 0.5 to 2.5 centimeters of water per liter per second. So in this case, we have a profound airway resistance problem. And we could think back to Poussey's law there, as far as what could be causing that problem. Maybe the tube's too long. Maybe the gas is too viscous. For right now, let's not worry about this one, but we'll come back and visit this another day. But it's a different way to express tidal volume if you measure the inspiratory flow rate and the inspiratory time. But I'm just going to skip over that for now. This one we do need to know, though. It's going to be one of our exercises today. If I know what their ideal body weight is, I can calculate what the normal range of tidal volumes is. Normal range of tidal volume. Yeah. So first of all, I got to convert that 120 pounds to kilograms. That sounds like a good question for this afternoon or for later on today. Just saying. 120 pounds times 1 kilogram divided by 2.2, that's our factor, conversion factor. Then we get 54.5 kilograms. I then multiply that 54.5 by 5, multiplied by 8, and that's my tidal volume range. Okay. So I might ask, which of the following tidal volumes would be within the normal range for a patient who weighs, whatever, 125. Okay. And one of the things you'll do today is go ahead and determine what your tidal volume range is.
Yeah, I don't get it.
You don't get it.
Well, what about the 5 minus 8 one?
5 to 8.
Oh, okay, got it.
2. Yeah, it's minus 3 milliliters per kilogram. Yeah, I know.
You never
How can you have a negative tidal volume? No, it's
You
sucking the
never
air
know.
out of me. Hold on.
Anything is possible with this.
I just make stuff up as I go. You know that. Okay? Minute ventilation. Minute ventilation is the respiratory rate, the frequency times your tidal volume. So here I have a given tidal volume of 700 and a respiratory of 20. Calculate the minute volume. Basically set it up as 20 breaths per minute times 700 milliliters per breath. And I come out with 14,000 milliliters per minute. That's kind of an ugly number. 14,000. What if I just say 14 liters per minute? And recall also that I can take this and solve for tidal volume or solve for frequency. One of my students a few years back showed me this, so I'll share it with you. I want to solve for this, frequency times tidal volume. I want to solve for that, minute ventilation divided by tidal volume. I want to solve for that, minute volume divided by frequency. She passed, so I guess it was a good thing. So that is the kind of problem that we're going to work with today, because we're going to solve for our average tidal volume. We're going to solve for this. We know that not all the tidal volume goes to an alveolus. Some of it's trapped in the airway, not participating in gas exchange. How rude. So what we need to do is figure that's about 1 milliliter per pound of ideal body weight. Oh, look at that rat bastard, what he did. Given an ideal body weight of 54.5 kilograms, calculated dead space volume. You have to convert that back to pounds, which is about 120. We just did that. So a person who weighs 54.5 kilograms or 120 pounds has roughly 120 milliliters of anatomic dead space. I just threw an ugly word in there, but you can ignore me.
So one of the ideal body weight in kilograms and one in pounds?
You can express it in either.
Like
Oh yeah, oh yeah. Just which system are you using? The metric system, or are you using the conventional system? Foot, pound, seconds, and okay. Okay. Alrighty. Not all that tidal volume that went to alveolus, but some did. And the question is how much. And for this, we just have the alveolar volume is equal to the tidal volume minus the dead space volume. So if I gave you a tidal volume of 500, and I gave you a dead space volume, or I told you that the person had 150 pounds of ideal body weight, you would know that there's 1 milliliter per pound of ideal body weight. I then calculate that out to be 350 milliliters.
I like that one.
All righty. Now, since you threw that wrench in there, agreed? Just rearranging that? Okay. You asked for it. Alveolar minute volume, then, is the tidal volume minus the dead space, what we just determined, times the frequency. So again, I have a whole bunch of information there. Tidal volume of 800, dead space volume of 200, respiratory rate of 20. 800 minus 200 is 600, times the 20 is 12,000 milliliters, or more commonly expressed, 12 liters per minute. Stop the madness. Okay. Let's see how this all fits together then. I'm going to skip that one. So what we're going to do is use a device called a respirometer. And a respirometer simply is basically measuring the amount of volume that is passing by a little sensor. Okay? And I think we just have the one type. But basically what they look like is something along this line. So that as I blow through, a little needle turns. And it's just like a clock goes around once and the other ring moves one in the process. And there's a little reset button there. Okay. We're going to work, break into groups of 3 or 4, or however many you want to. Doesn't matter to me. And I have a worksheet that you're going to complete for each of you. Okay, this out first. You guys don't look happy. Like you got a test sitting or something. When did you guys get into groups? It's a group. Okay, good. You guys are a group? Sure. Now, if you notice, these have a rubber outer. So that if they're dropped, they don't get destroyed. Because they're very expensive. All right, so I think you guys all have the halo scale, right? This one? Does it look kind of like that? So you have 2 dials, one on the outside, one on the inside. The inside, if it goes around one time, that's 1 liter, which should click then the outer rim for the second one. You follow my gist? Goes around the clock one time. It's kind of opposite of a clock though, because the inner one moves around once and the outer, the long arm clicks once. So you gotta kind of reverse your thinking there a little bit. So if I was counting this, what this minute volume was, I go here and I go, so this is almost to 13, this is almost back to the top. So I would call this 12.92. See how I read that? If not, it's okay, I'll come around and read it for you, but almost to 13, almost back. So once this goes across that line, this will be at 13. So it's something just shy of 13, 12.912, 0.92. Okay? All right. So this is the, let me just stop the recording on this, so we don't need this.